Hello once more. And, Thank you for coming to my session on which is probably for most people quite esoteric topic because most people do not build their own cryptographic solutions from scratch. But perhaps you still want to know, I presume, how this is done in case you do need to do it. And so this is what we are going to discuss here today. So my name is Ahto Truu. I work as a software architect in a company called GUARDTIME, and the software architect title is a little bit outdated. I have recently been drifting more into a researcher position, and this is also the direction the talk is going to take in the end. A little bit about GUARDTIME. We are a systems engineering company focusing on data security solutions. And in particular, we are running one of the world's oldest and biggest blockchains. The company was founded in 2007 in Tallinn, and our blockchain went into production use in 2008. So it is a year older than the well-known Bitcoin blockchain. And nowadays, legally speaking, our global headquarters are in Lausanne, Switzerland, but we have offices in outside of Europe, also in US and China. And the majority of the engineering and research work is still being done in Estonia. We now have offices in Tallinn and also in Tartu, which is where I reside. We are currently about 150 employees, and around 80% of those are actual engineers and researchers. So it's quite tech-heavy company, and for a company of that size, I don't think it's a very small feat that we have a dedicated research team of 7 people, one of which is myself. And I guess that's it for the introduction of the company, and let's see what we are going to talk about today. So. First, I try to give a very quick overview of the main things or main primitives used in cryptography. And then from there on, we will focus on digital signatures more specifically. And then because the talk is going to be about how to build signatures from hash functions, then we go into some details about hash functions. And then we start seeing how the digital signature systems could be built from hash functions. And we look at this from several aspects. First, some historical hash function-based signatures, then hash function-based timestamping, and then how timestamping can be combined with other cryptographic tools to obtain a signature scheme or a signature solution named VLT, which is reason I am giving this talk today. So with that roadmap ahead of us, let's get started. So the introduction into cryptography. So when hearing the word cryptography, most people seem to think about encryption first, which is art and science and technology of making information unreadable to unauthorized parties. And historically, the oldest and best known encryption systems have all been in this family, what is called symmetric encryption. And the symmetric part, the encryption itself is used if I want to transfer some document or some message over a channel which I don't trust, then what I do, I encrypt it. So I change my plain text or my clear text into something unreadable, some gibberish, which is called a ciphertext. And then I can send the ciphertext across this unprotected channel to my recipient, who will then apply another algorithm to it to decrypt and obtain the clear text that the recipient can read. But the main idea is that in transit, this encrypted data is like it would have been wrapped into a non-transparent envelope. So whoever observes it, they can't read the contents. And the symmetric part in this term, symmetric encryption, comes from the side that the secret key that is needed to encrypt the message is exactly the same as the key that is needed to decrypt. The encryption and decryption algorithms themselves may be the same or different depending on the system that is used. but the key, the critical part is the key is the same, which means that if I want to send encrypted messages to somebody, we have to previously somehow share a key. We have to somehow establish a shared secret so that when I encrypt something, the recipient can decrypt it successfully. And as you might guess from this notion of symmetric encryption, there is also corresponding notion of asymmetric encryption, also known as public key encryption synonymously. And the difference here is that every recipient has a private key, and every private key has a corresponding public key, and the public key can be published, like a phone number in a phone book, which is a classic textbook example of explaining the meaning of a public key. And now the private key and public key are related to each other in such a way that a message that is encrypted with one public key can only be decrypted with a corresponding private key. So any other private key will not work for decryption of this message that has been encrypted with one specific public key. And this means that if I want to send a message to somebody, I don't need to have a prior arrangement with them to exchange the secret keys to establish a shared secret key. I can look up the public keys. I can publish a public key in a phone book or in a directory somewhere, and I can look it up. I can use the public key to encrypt the data, send the data away, and be fairly confident that nobody else except the holder of the designated private key can read my message. And while symmetric encryption schemes have been known and used for thousands of years, certainly Julius Caesar around 2000 years ago was using already very primitive by today's standards, but still asymmetric encryption scheme. The very notion of asymmetric encryption was proposed only in 1970s. So before that, people didn't even think something like that would be possible. And interestingly enough, in the very same paper where Diffie and Wittwit Diffie and Martin Hellman first posted the notion of having this asymmetric encryption in theory. They didn't have a specific construction of how to achieve it. This came about 3 years later. First successful asymmetric encryption scheme was designed by Rivest, Shamir, and Adelman. It is known as the RSA crypto system, and it is in quite wide use even today. And but already in the very first paper, Diffie and Hellman also considered the notion of producing digital signatures, which is kind of, you can look at it as a public key encryption applied in reverse. And indeed, in case of RSA, for example, it is exactly. So the algorithms are exactly the same, even if the labels are different. So you still operate with the private keys the same way as for decryption of data, and you operate with public keys the same way as for encryption of data. But you do your setup slightly differently, and the result is that you can combine in so-called signing algorithm. You can combine your documents that you want to sign with your private key. Basically, you operate on your document with your private key, and this adds a tag to your document. So the document remains in clear text. Everybody can read it, but it now comes with a tag. And now anybody who has access to the public key can run the tag document, the tag, and the public key through a so-called verification algorithm. And this will tell if the tag was indeed computed for this document using the corresponding private key. And so assuming that the signer is in sole control of the private key, that nobody else has a private key, then if this verification passes, this is evidence that the document really came from somebody who controls or has access to this private key, and the document hasn't been changed en route. So the document is what was signed, and this is in digital signature frameworks. Then this kind of applying a sign with your private key or applying a seal with your private key to a document is considered equivalent to signing it by hand, by writing your name on it, or maybe more appropriate analogy is by actually sealing it. If you recall from history, the wax seals on various documents applied to them to indicate agreement or to authenticate the origin of a document. So in some ways, the digital signature is more similar to a wax seal applied to the document. I will not go into much more details about cryptography in general. There was a pretty good overview of cryptography for programmers given by Daniel James in this very conference in 2018. So if you want to have more background, more technical information about symmetric, asymmetric encryption, specific algorithms in use today, libraries, things like that, I recommend you check out his talk. It's full of useful practical information and also more details about how RSA works for encrypting documents. But today we are not going to do that, because if I were to go into more details about crypto in general, then we would not have time to cover the parts that are in the title and in the abstract of the talk. So we will focus on digital signatures. So to recap what the digital signatures are and what is their purpose. So they aim to be the electronic equivalent of handwritten signatures or sort of physical wax seals on documents. And the intent is to show as a signer's endorsement, or to indicate the signer's endorsement of the content of the document, of whatever was signed or sealed. And in order for this to be meaningful, there are more detailed technical requirements that they have to fulfill. So they have to protect the integrity of the document or the contents that was signed, because if it is possible to change the document after it was signed, and then the signature would still be valid for this changed document, then clearly this has no value in expressing the endorsement, because if I agree to the original document, this does not necessarily mean that I agree to the changed version. So it must be the case that when the document is changed, the verification against the signature and the key will not pass anymore. So and the goal then of course also is because intent is to indicate endorsement by the signer, the goal is also to be able to establish who is the endorser. Again, the endorsement is not worth much if you don't know who was endorsing it. And for legal, and actually in case of digital signatures also for technical purposes, in many contexts there is also a need or requirement to be able to establish authenticate the signing time to know when the signature was applied to the document. For example, if I sign something as a member of a board of a company, then legally speaking, this signature as me, as in the role of this office, is only legally valid during when the signature was made during the time when I actually was a member of the board. I myself personally, I physically I may be able to sign papers after and before my term in the office, but they would not be valid. They would not be binding for the company if I would do it while I'm not in the position of a board member. And one thing that is also a requirement, but is maybe a little bit tricky to realize at first, is a property of non-repudiation. So the idea is that once I have signed something, I cannot deny that I did sign it. So in other words, this means that this means that the document can potentially be used as evidence against the signer after it has been signed. So this is essence of what basically what we want from digital signatures in order to replicate the functionality of handwritten signatures in the real world. For digital signatures, there are two main use cases, depending on what you want to do with the result. So as a relying party, they have two functions. The relying party first, the recipient of a signed document can first verify for themselves that the document came from where it should have come and hasn't been changed since. And then they can also prove this the same to some third party. So I can verify myself that the request or document or whatever came from the correct correspondent, and then I can prove this to somebody else. And the main use case types for these kinds of things are in IT systems are document signing, which is what we have been discussing or what I have been discussing here mostly so far, and also for access control. So access control means that I can sign with my private key a request to be let in or to be granted access to some information system. And this is essentially what happens when you sign into an IT system with an SSH key, for example, SSH private key. So the server sends you a challenge, and you sign this challenge to prove that you hold the corresponding private key, and then the server verifies the signature on this challenge to check that you actually do control the private key. And based on that, will let you in or will not let you in, depending on whether the signature verification comes out. And in document signings, and then this also means that for access control, the main purpose of the signature is that the server can verify the authenticity of the incoming request for itself, so that it knows the request can be processed and honored. Whereas in document signing context, typically the intention is that I will file away the signed document so that I will have it available as evidence if I need later to prove to somebody that this document was indeed signed to the appropriate party. So there are technical differences, and there are also philosophical differences in the meaning of the signature in those two use cases. But the solutions can be used for both. So the mathematical model for digital signatures, we already mentioned it very briefly in the introductory slide. But to recap, then each signer has two related keys. One is private key for gating signatures, and another one is public key for verifying signatures. And the signature scheme, so-called, this is a technical term that is used in cryptography. A signature scheme consists of three algorithms. So first is key generation, which generates a new pair of related keys. So you use a key generation. This is a randomized algorithm to generate a new pair of keys, a private key and a corresponding public key. Then you keep the private key private to yourself and share the public key with everybody who needs to have them, or just publish it into some directory. And then there is a signing algorithm, which was oval on the left-hand side on the overview slide, which gets as input a document and a private key, and then produces a signature as output. And then the document and the signature side by side can be sent to whoever is intended recipient. And then the verification gets a document, a signature, and a public key. And then the verification algorithm basically says yes or no, whether the signature was created with the corresponding private key, with the private key corresponding to the public key that was given as one of the inputs to the verification algorithm. And note that the public key is only the input to the verifying, and the private key is not needed for that, because the private key must be kept private by the signer. Otherwise, if the private key would leak, then anybody would be able to produce new signatures in the name of the signer, and then the whole exercise would be quite pointless. And we get then to the security model, which I already briefly mentioned before. So for a signature scheme to be usable and secure, it must be infeasible for an attacker to change a document without making the verification fail. And since the security depends on only the signer having access to the private key, then it should be infeasible for an attacker to derive the private signing key from the public verification key, because the verification key is a public key is intended to be publicly available to everybody who wants to verify the signatures, and so there it must be impossible to derive the private key from the public key. And it also must be impossible to create a signature without access to the private key. So these three are the main requirements that a signature system must satisfy in order to be secure. And then we need to make sure that any unauthorized parties cannot access the private key. And this the best practice, if possible at all, is to generate the key pair in a secure hardware module and export only the public key from the module and keep the private key inside the module to never leave. And for signing, then it's not the case that the private key is taken out of the module. The signature is produced in some general purpose computer. But the best way is that the data to be signed is sent to the module. The signature is produced in there in a controlled, protected environment. And then the signature is exported. But again, the private key never leaves a secure environment of the hardware module. So this is the preferred way. If this cannot be implemented, then this also can be sort of simulated by keeping the private key in a very restricted controlled kernel, software kernel, and then having other parts of the software system request signatures from this protected kernel. This is another way to reduce the attack surface that adversaries could be taking advantage, could be using to attack the system and to obtain the private key to be able to then forge signatures. One thing that we also have to mention, even though this is from the actual digital signature algorithms, from the cryptographic point of view, this is on the next level of the protocol, is that we also need to have some way of establishing the signer identity. So a public key is just a piece of data. In most crypto systems, this is a large random random looking number. And then if we want to authenticate the origin of the data, then we must have some way of binding a public key to the identity of the key holder or the key owner. And the key holder, then how do the verifiers know which public key corresponds to which key holder? So there are three main models for that. So first one is that the key holder can hand the public key directly to the relying party. And this is mostly used in access control systems. So basically, if I want to be able to access a server, then I generate my private public key pair. And then I personally hand my public key over to the administrator of the server, which then adds my public key into the list of authenticated, into the list of authorized keys. And then the server knows that anybody who has the ability to sign with a corresponding private key must be me. And so this is handling of this identity is done by I talk to the relying party directly. I say, this is my public key. I take responsibility for whatever is done with the corresponding private key. And then based on that, then the key is added to the trust list. Then this, of course, it doesn't work in all contexts. Like if I cannot meet the recipient in person, then it doesn't work. So for that, two main kinds of solutions are proposed. So the first one is that the identity of the key holder is witnessed by someone the relying party knows. So if I want to correspond with somebody, then and we have a mutual friend, then I can give my key to the friend, and the friend can give the key to his friend, and so I can now send messages, side messages to this friend of a friend, which I maybe haven't met personally. So this system is called the so-called Web of Trust, and this was used in the BGP framework, which was one of the first publicly used public key cryptography systems starting in 1990s. And then a more like business view of it is that that identity of the key holder is witnessed by a designated authority. So this is kind of like having your contracts or your signature notarized by a notary public. And those designated authorities, the technical term for them is certificate authority. And this is used in the so-called PKI model, which stands for public key infrastructure, where certificates are statements binding public keys to the identities of the key holders. And those certificates themselves are digitally signed by the certificate authority. So in order to bootstrap this system, I need to somehow obtain the public key of the certificate authority so that I can verify the signature of the certificate authority on the certificates that they have issued. And then by this proxy, I can start trusting the public keys in the certificates as to who their corresponding key holders are. And this is a system that is most widely used in business settings today. I see there is a question which maybe I can answer right now. The question is it possible for the key pair generation to accidentally produce a random key that is mathematically solvable? So this depends, I should say, on the specific cryptographic system that is used. In general, there is no such thing in cryptography as impossible. Everything is a game of probabilities. But everybody tries to set up their system in such a way that the probability of a successful attack is so small that we can basically discount it. The technical term for it is that the probability is negligible. And the way how those negligible probabilities are measured is usually that the probability of the attack is 2 to the power of minus something, or alternatively, you have to do 2 to the power of something operations or 2 to the power of something attempts to be successful in your forgery or in your attack. And this to the power of something, this is called usually the security level of the crypto system in bits. And for commercial applications, generally a security level in 100 plus bits is considered good, which means that in order for an attacker to be able to break the system, they would have to do a computation in the amount of 2 to the power of 100 operations. And this is considered infeasible for anything in real life. So 2 to the power of 100 really is a very large number. I have a memory lapse right now. I don't have a good thing to say of something that is in real life is 2 to the power of 100. But this really is a huge number, and it is generally accepted that nobody can afford to spend that much computations to break anything. So then for signing time, I already briefly mentioned that for legal reasons, it is often necessary also to verify or prove the signing time of when the signature was created. And this is also needed for technical reasons. So if, despite all your precautions, your private key is somehow compromised, leaked, somebody obtains a copy of the private key, then you want to be able to revoke the key. You want to be able to disown the key, and anything that is done with a key in the future, you don't want to be responsible for that. But if you just could cancel your key, then this would be an easy way for you to get out of any contract that you have signed that you don't want. So what is needed is that when you declare your key no longer valid, anything that you had signed before, all the signatures should remain valid. And anything that's now that whoever stole your private key is forging the signatures in the future with your stolen key, they should be invalid. So, and for that, there is also, this is something that does not happen in real world. When you do a pen and paper signature or an ink signature, then the signature is, the essence of the signature is that you have applied your biometric specific, your biometrics to produce a signature, your unique handwriting traits. And this is something that nobody can steal. They may be able to copy the image of the signature from one piece of paper to another, which is a different story. Or they may be able to forge the look of your signature in such a way that a casual observer will not be able to tell the difference. But they cannot inherently steal your biometric identity. So this does not really happen in ink signatures, but in technical signatures, because the private key is a piece of data, then maybe embedded in some hardware, maybe kept in some file on your computer, maybe protected with a password, maybe not. So there are chances that this piece of secret data can be copied and you no longer control it. And then you want to be able to revoke this key, that is to prevent anybody else from creating valid signatures with it in the future, and to be able to tell the difference. And there is a technical reason also why we need to know the time when a signature was created. So this, I hope, wraps up the general discussion about what digital signatures are in and by themselves. And now we can go to hash functions, which is another cryptographic primitive besides symmetric encryption, asymmetric encryption, and the digital signatures. And we haven't talked about those so far at all. So probably everybody here knows hash functions as something that you use in database theory or data structures. We have hash maps and we have hash sets and things like that in C++ standard library. So this notion of hash functions is really from 60s, based on needs of data management, of data structures databases. But hash functions are also used in cryptography, and the first level, the requirements of hash functions the requirements to hash functions in cryptography are similar to those in the database system. So you want to be able to take basically any input and compress it into a fixed size fingerprint that is called a hash value, or in cryptography also a message digest. And then the intention is that this fingerprint is a representative of your data. And this is actually how pretty much all signature systems are implemented in practice. So I have taken here the model that I have my private key in this cryptographic token in this chip on a card. This is actually a publicity shot of the Estonian national ID card. So pretty much everyone in Estonia walks around with one of those in their pocket. And inside this chip, there is a private key that I can use to make a legally binding signature. And the way, like I said, the preferred way for handling private keys is that they are generated inside a secure hardware element, this chip in particular in this case. And the key, the private key, always remains inside this chip. It never goes out. So if I want to sign a document, then the model is that instead of taking the key out to sign it, I pass my document into the chip, and then the chip produces a signature and returns me the signature, but does not ever reveal the key. And now there are two things. First, the chip is a very weak computer, so if I want to sign anything large, this would be very difficult for performance reasons. So and the solution is that instead of the document itself, a hash value is computed, or a fingerprint of the document, and then this compressed representation is sent to the chip, and the chip does not sign the document directly, but indirectly by signing the hash value. And more fundamental reason for doing it this way, besides performance, is the performance actually is just a nice side effect. the more fundamental reason is that most digital signature systems, and this includes RSA, this includes elliptic curves based systems, which are the two main families in use today in the world. They cannot operate directly on data that is larger than the key. And in case of RSA, the key typically is a couple of thousand bits, which means it's a couple of hundred bytes. And in case of elliptic curve-based systems, even actually the key is smaller, so it's a few hundred bits, so it's a few tens of bytes. And this is the largest value that you can sign directly. Now, if you go and open Microsoft Word and create a new document, and without typing a single letter into this document, just save it. This blank document is around 16 kilobytes. So this is already too large to be signed directly by a normal RSA or a normal elliptic curve-based private key. So this is the main reason why hash functions are used, even in signature systems where the signing algorithm itself is not based on hash functions. So let's look at the hash functions. So I already briefly mentioned that the primary requirement is that the arbitrary input data can be efficiently compressed into a small fixed size representation, like in the hash functions that we use in data structures. But additionally, in cryptography, we have more requirements because we want to use hash functions as representatives of data. And in more technical terms, the word in cryptography is commitment. So we want to be able to indirectly commit to some data via its hash value. So the first requirement is the same as in database systems. So a hash function has to be efficiently computable. So because the data that you want to sign, they may be large. You may want to sign a PDF file of a few hundred kilobytes. That's no problem, of course, with anything. But you also may want to sign for authentication, for example, a virtual machine image of a few gigabytes. And so you really want the hash function to be efficiently computable in the forward direction. But you want the hash function to be one-way, so-called pre-image resistant. So this means that given a hash value, it should be infeasibly difficult to find an input, so that if you apply the hash function to this input, you get a predefined hash value. A model that you might want to have for this kind of thing is, so for example, consider that you want to you want to place bets on the result of the football match this weekend in office, and then what you can do is that everybody puts a prediction in a file about the result and computes a hash value and posts a hash value to the company chat in Slack or whatever chat tool you're using inside. And then when the weekend comes and goes, on Monday, there is time to open the predictions to see who predicted correctly the result of the match. And then what you want is that if somebody in the office is considered an expert on football, you want the property that whoever is looking at the hash value that was committed into this chat, that they would not be able to reverse the function to find out what this expert predicted what the result is, that they have to make their own prediction independently. So in case, and this also brings us to one thing, that the hash function itself technically may be one way, such that it is very difficult to reverse it. But this one-wayness is only applicable if your input data has sufficient randomness or has sufficient entropy in it. And this is generally not the case with football results, because it's very rare to have a football game where one side gets more than 10 goals. So basically, you have 11 possible results for the home team from 0 to 10 goals, which is in the realistic realm, and actually 10 is not very realistic from what I have seen in football. And the away team or the visitor team can also have from 0 to 10. So altogether, you have 11 by 11, 121 possible results. So if you just take the two numbers as your prediction and hash them and post, then no matter how secure your hash function is, what the other guys in the office can do, they can do this so-called informed brute force attack. They can just try all possible reasonable results, 0, 0, 0, 1, 0, 2, 1, 0, 1, 1, 1, 1, 2, and so on, and see which one of those predictions, if they hash it, matches what you posted, because the hash function is deterministic. If they apply the hash function to the same input as what was your prediction, they will get the same output, and then they can verify still what your prediction was. So this premise resistance property is only possibly strong and useful if your data contains sufficient entropy. And there are ways, if your data actually does not contain sufficient entropy, there are ways to add entropy artificially. For example, instead of typing into your text file that my prediction for the game is 1 to 1, you can say, and you can add on a second line, and by the way, a large random number is blah, 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 and then put a large random number in there. And now, if somebody wants to do this kind of trial and error attack on your posted hash value, then what they have to do, they have to guess not only what was the results that you predicted for the game, but they also have to guess the large random numbers that you put into your file. And then on Monday, you can still prove that your prediction was correct by showing your file, which contains both the prediction and the random value. And so anybody who has access to this file can verify that this actually matches what you posted, the hash fingerprints that you posted on Friday. So your prediction is still verifiable, but it's no longer amenable to this brute force attack. So this is something, again, it's kind of thing that when you do design cryptographic protocols, you have to think. Just because your hash function is strong one way, this doesn't mean that your input data cannot be reverse engineered from the hash value if the input data itself is too easily predictable. Another property that people want from hash functions is second premise resistance, which means that if you have one input, then of course you can apply the hash function to it and compute the corresponding hash value. And then the second premise resistance property says that it should be infeasible to find a different input that maps to the same output using a hash function. So this is basically the property of hash functions that enables the use of hash values as representations of data, as commitments of data. And this goes to the properties that if you want to do this document signing not by signing the document directly, but by signing the hash value of the document instead, then it must be infeasibly difficult for an attacker to change the document in such a way that the hash value is the same as before. And this, because this would enable the signature to be considered valid to this modified document. So if the signing goes like on this slide, where you start with a document, you hash it, and then you sign the document indirectly by hashing it. So whoever is able to change a document in such a way that the fingerprint of the modified document is the same, then the signature really applies to both documents equally well. And this is what we want to avoid, and this is why we demand that the hash function that we use must be second premise resistant. The hash function also has to be collision resistant, which means that it must be infeasible to find two different inputs that map to the same output. And now, on first glance, this might seem like, okay, we already have this property. What is the difference between the second premise resistance and collision resistance? And this is actually a trap. So these are actually very different properties, cryptographically speaking. The key difference here is that the attacker is able to choose both inputs, whereas in the second premise resistance property, one of the inputs is fixed, and the attacker only has freedom to choose the other one. And it turns out that this flexibility gives really a great advantage to the hacker or attacker. So if you have a hash function with n bit outputs, then there are 2 to the power of n possible outputs of the hash function, and it is possible to show that an upper bound on the second premise resistance of a hash function is 2 to the power of n. So if an attacker is able to generate 2 to the power of n possible inputs, then they can do the premiss resistance attacks. And if you just try 2 to the power of n random different x primes, then with high probability, one of them will map to the same hash value as original x that was given. So this is kind of roughly in the not the same, but somewhat similar to what Bitcoin mining is, where the miner just generates random numbers and computes hashes, and then until one of the hashes has the required format. So it's not exactly a fixed value that they are targeting in Bitcoin mining, but a fixed format of the hash value. So a subset of hash values is acceptable. But basically, brute forcing this weakened version of this premiss is what Bitcoin mining is about. And in collision resistance, then it is possible to show that if you have an n-bit hash function, then the upper bound on how difficult it is to find a collision for this hash function is not 2 to the power of n, like in case of the second premiss resistance, but 2 to the power of n over 2, or square root of 2 to the power of n. And this means that if you have a hash function with 256-bit outputs, which is common and standard practice in today's cryptographic systems, this means that the second premiss resistance attack is expected to cost around 2 to the 256 operations for the attacker, but collision resistance attack is expected to cost about 2 to the 128 for the attacker. And this is really a huge difference in difficulty. And there are also different cryptographic scenarios in which if you can do one kind of attack on your hash function and cannot do another kind of attack, then what kinds of attacks are possible when the hash function is used in the context of digital signatures? So if we consider the story where Bob wants to get some money from Alice alone, and then writes an IOU note. So Bob creates a contract which says that I owe Alice $10 and signs it by first hashing the contract and then signing the hash value, and then gives a signed contract to Alice, and then Alice gives Bob the money. And then when the loan comes to term and Bob has to pay it back, then what the second premiss attack, if the hash function used is vulnerable to second premiss attacks, then what Alice can do, the documents that she got, the IOU notes that she got from Bob, she can modify it to say that Bob instead of $10 owes $1,000 to Alice, and presents this modified document. And if the modified document hashes to the same value, then Bob's signature on this modified document is also applicable and valid to the other document. And now Alice can claim that Bob signed this other document instead, and can demand that Bob pay back a lot more money than is necessary. So this second premiss resistance, or rather the lack of second premiss resistance in a hash function, enables forgery of signed documents after they have been signed. But the collision resistance comes into play if whoever creates a document in the first place is malicious. So suppose now the same thing, Bob wants to get some money from Alice, but now instead of Bob creating the IOU note and signing it, it's Alice that prepares the contract. And Alice can prepare two contracts where one says Bob owes me $10 and the other one says Bob owes me $1,000, and then sends the first one to Bob for signing. Bob signs it, returns the signed document, Alice gives Bob the money, and then when the loan comes to term and Bob has to pay it back again, Alice is able to, if the two documents have the same hash values, then Alice is able to produce a second document and claims that Bob signed this one and demands that Bob pay back more money. And now the difference here is that the forgery was premeditated. So the forged document, the second document, was prepared before the signing happened. And for this kind of attack to work, it is sufficient that the collision resistance of the hash function is broken. So in order for a signature system using signing via hash values to be secure, the hash function needs to be both second preimage resistant and collision resistant. If one of those two is not satisfied, then the hash function is not suitable to be used in this kind of hash and sign model of digital signatures. So now that we have established that pretty much all digital signature systems use hash functions anyway, and then the RSA and analytic curve-based systems, they use something extra for the actual signing part, then it is interesting to notice that actually you do not need anything else. If you have hash functions, this is all you need. You can build digital signature systems out of hash functions only. You do not need the number theory or the abstract algebra of elliptic curves, and you can do. So in some ways, you can say that building digital signatures out of hash functions reduces number of underlying requirements. And in some ways, you can say that these are signature systems based on minimal requirements, because it is possible to show that if there are no hash functions, no secure hash functions, then there are also no digital signatures possible. And now one thing you may have heard of and you may want to wonder is message authentication codes, hash function based. So what you can do with a hash function easily is to authenticate messages. So this is kind of the symmetric. If you recall from the first couple of slides, the distinction between symmetric encryption and asymmetric encryption, where in one case you have the same key on both sides for encrypting and decrypting, and in other case you have the different keys, public key for encryption and private key for decryption. Then the message authentication codes are the symmetric key equivalent or the symmetric key brother to digital signatures, where the signing key and the verification key are the same, just as encryption and decryption keys are the same in symmetric encryption systems, whereas in signature systems and asymmetric encryption systems, the two keys are different. And how you can construct message authentication codes from hash function is you just take your document, you add your private key, you concatenate those two together and hash them. And the resulting hash value depends on both the key and the document. And so if you now send the document with an authentication tag attached to it, then whoever has the same key, what they can do to verify the hash function based tag on your document is they can take their own key and the documents that they have received, they can reapply the hash function to the concatenation, and then they can verify if the tag is the same as what they got. If it is, this means that the document came from somebody who knows the correct key and the document hasn't been changed in transit. So it kind of looks like digital signature. I can verify where this document came from, and I can verify that it hasn't been changed. And it is, if you think about it for a moment, it should be pretty clear that this is actually a secure thing. If assuming the attacker does not know the key, if they want to change the document here, and if they would want to recompute the corresponding tag, they would have to apply the hash function to the combination of the modified document and the key. But they don't have the key, and this means that they can't update the tag to match a modified document. Assuming the hash function has all the preimage resistance, second preimage resistance, and collision resistance properties. So this is secure. One thing that it is not a digital signature, and it is not a digital signature because it lacks the property that the recipient would be able to use this signed document as an evidence against the signer or the sender. The recipient in this model, in this case of message authentication codes, is not able to convince a third party, somebody else, that the document came from the sender. And why is that? This is because the recipient knows the same key. So the recipient can make up any document and can apply the key to the document to compute the corresponding tag. And this result is indistinguishable to anybody from the case when the document and the corresponding tag were indeed created by the claim sender. So a third party verifier, like a judge, will not be able to tell the difference between something that the sender has sent and authenticated, and the difference between something that the recipient made up themselves and then tagged. So the recipient, if they know that they did not tag this particular message, they can, for themselves, they can verify that the message came from the sender, but they cannot convince that this is the case for any other party. And this means that the message authentication codes are authentication system, but they do not provide non-repudiation. And curiously enough, the first actual construction of digital signatures was actually based on hash functions or one-way functions, as they were called. The term hash function has not been applied to cryptographic context at this time yet. This came a bit later. But this idea was actually the very first paper by Diffie and Hellman, which was published in 1976, which is 3 years before RSA was invented. So hash function-based digital signature systems are actually older than the RSA-based ones that we are using today. And the idea roughly is that if you want to sign a one-bit document, so you want to sign a one bit, which can be a 0 or 1, then what you do for private key, you generate two random numbers, x0 and x1, and then you compute the hash values of both them. So y0 is hash value of x0 and y1 is the hash value of x1, and you publish this pair as your public key. Now, this is something that you do in all systems. You generate the key pair, the private key, public key, you publish a public key, and then you wait until you need to sign something. And now, if you want to sign the bit value 0, what you do, you publish as your signature, or you enclose with the bit value 0 as your signature, you enclose the value x0. And if the value of the bit that you want to sign is 1, you enclose as a signature with the bit 1, you enclose the value x1. Now the recipient who receives this 0 with x0, what they can do, they can take the x0, hash it, and verify indeed that it matches the first component of the public key, which is the authenticator value for the 0. And so they can verify that the signature matches the document or the value that was to be signed. And if this is not the case, they will reject the signature as invalid. And likewise for bit 1. So this is how you sign one-bit messages using a private key consisting of two random values and a public key consisting of two hash values of those random values. Now, what if you want to sign a longer input? Because normally, well, in some cases, if the message that you want to sign is just yes or no, one bit will be good enough. But oftentimes you want to sign something longer. Then what you do is you do a batch of private keys and a batch of corresponding public keys, and you can sign each bit of your inputs separately. And this is perfectly secure. The only problem, well, actually two problems with this system is first that the signatures are quite large. So if we're talking about 256-bit hash functions, then each of those components in this public key is 256 bits or 32 bytes. And if we take this hash and sign model, then the hash value that we need to sign, the hash value of the document that we need to sign is 256 bits itself, which means that we need 256 of such how do you call it? It's not couple. It's quadruples of values. And the result is that the private key and public key, each of them is 16 kilobytes large, and the signature is 8 kilobytes large. So this was when this idea was proposed in back in 1976. This seemed like impossibly large. Nobody wanted to take such overhead. This may look quite a lot more reasonable today, given how large amounts of data we are pushing around in the network anyway already. So this might be okay. Another serious limitation is that this signature scheme is one time. So you have created one private key and one public key, and you can use it to sign one document. If you sign more documents, then an attacker would be able to take some of the 0 bits from your one signature and some of the 1 bits from your other signature, and then combine them and obtain signatures on other values that you did not sign. And so they would be able to forge signatures on at least some values. So it is in this case critical that you use one private key only once to sign one document. And we come back to how to get around that in a moment. I'm starting to get a bit behind my time, so maybe I will skip detailed discussion of internet signatures, which is a way to reduce the signature size by making the whole thing a bit more complicated. But the name internet is really distinctive. If you want to look it up later, you can just do an internet search, and you certainly will find explanations of how the internet signatures work. So I will skip this for now to keep time. And now the thing how you get around these limitations that both LAMPORT signatures, which I described, and the internet ones, which I just skipped, they are one-time signatures, one-time schemes, meaning that you can use one private key to only once to sign one document. So what you can do in order to reduce your costs of distributing keys is you can generate a bunch of key pairs, and then aggregate the public keys into an aggregate value, and then publish this aggregate value with your as your public key. So you can get this two-level or two-step system. So where instead of publishing your public key or your set of public keys directly, you publish a commitment of a set of public keys and say that anything from this set counts as my public key. And then if the signature is made with a corresponding private key, I'm still responsible for all of them. And the aggregation mechanism is so-called Merkle tree, which was also invented in late 17th. So it seems everything we talk about today is some 50 years old now. And the idea is this is kind of like how to take a regular hash function, which takes one input and maps it to a hash value and put it on steroids so that the hash function can take a large number of inputs and map them still into one hash value. And the idea is that if you want to aggregate a large number of inputs into one single hash value, you build a binary tree, and the inputs that you want to hash, you line them up in the leaves of the tree. In most applications, the values in these leaves are themselves hash values. So if you want to authenticate other data, which are not hash values, you first hash each data item separately, and then you line the hash values of the inputs up in the leaves of this binary tree, and then you populate the upper levels of the tree by populating each non-leaf node in this tree with a hash value of the concatenation of the nodes. So you get on this level, you get half the number of nodes, and after a logarithmic number of layers, you get to the root of the tree. And here now you have one hash value, and this one hash value indirectly represents all of the inputs. Because if you afterwards want to prove that one of the inputs was part of the set that was aggregated, what you can do, you can show as your proof this path through the tree. So if I want to prove that x3 was part of the set that I aggregated into this one hash value, what I can do, I can redo the computation steps. I can start from x3 and here and go here and go here. So I can redo a slice of the computation of the tree. And if all of the steps are done using a collision-resistant one-way hash function, and the end result comes up the same as the original value of the root of the tree, this is actually very strong proof that x3 was the original member of the original value of the leaf in this tree. And in order to be able to redo those computations on each step, I need the sibling hash value here. So I need to supply as a proof of membership for this one value. I need to submit additional information, which is logarithmic in the size of the original set. And so this is what hash trees or hash tree proofs are all about. And Merkle actually invented them in the 70s exactly for this purpose, that if you want to turn a one-time signature scheme into a many-time signature scheme where you can do many signatures, you just generate a bunch of one-time private keys, you generate a corresponding one-time public keys, and then you aggregate this set into a Merkle tree, and then you publish this as your public key. And now if I want to sign one document, I use the first one-time key there to sign this document. And in addition to whatever normally goes into my signature, I also enclose this hash proof that this actually was one of my keys originally. And then I have to remember that I have already used up this key and I can't use it anymore. So if I need to sign a second document, I just use a second one-time key and so on. So this is workable, but still you need to generate a lot of keys in advance, and the signatures are quite large. And this is mainly the reason why hash function-based signatures are not so popular, and RSA and elliptic curve-based so-called the elliptic curve-based so-called algebraic signature systems are more popular. We have a question. Doesn't the Merkle tree idea mean that your overall hash function must be much more likely to be subject to collisions? I think the intended question is that doesn't this aggregation make the whole thing more likely to collisions? It is true, yes. You need, in order to be able to guarantee a security level, you need to account for the size of the tree, because number of potential places where a collision can occur is larger, and you need to put additional restrictions either on your hash function or on the way you construct the tree in order to maintain a reasonable security level. But so it is a very good question, and the short answer, which I cannot really expand here much more, is that there are ways around that. So it's a valid concern, but there are solutions to address this concern. But the idea is, you can take a large number of inputs, you can aggregate them into a single hash value, and then for any individual input, you can later produce a compact proof that it was part of the original set. And now we talked about timestamping. So in the PKI world today, timestamping is usually based on this notarization model. If I want to timestamp something, I send my data, or rather more accurately, a hash of my data to a notary, and the notary writes down next to the hash value the date and time from his presumably accurate calendar and clock, and signs it, which basically means the attestation of the notary that this data was presented to me at this date, at this time. I act as a witness. Another way is if you want to prove the existence of some information, you can just publish it. And if the information itself is confidential, then you publish a hash value instead. And this is a model that I already hinted at when we were discussing this idea of placing bets on the result of the football game this weekend. So what you were doing by posting the hash value of your prediction into this company chat channel was basically publishing the hash value of your prediction in order to timestamp, in order to be able to, on Monday, to be able to prove that I made this prediction on Friday, but without revealing your prediction. So you didn't post your prediction itself, you posted the hash value. But this created the conditions for you to later reveal the underlying prediction and to be able to prove that this is actually what you predicted on Friday. And you did not make up your prediction on Sunday night after seeing what the actual result of the game was. So, and this idea of timestamping, interestingly enough, is very, very old. This kind of thing was used already by Galileo and Hooke back in 17th century. They did not have the hash functions of today, of course, and they did not even have the term, because the term hash function in cryptography, it was deployed in cryptography in the 80s and in database systems in the 50s or 60s, but all of it happened in the 20th century. So they did not have the term hash function, but they used something that was essentially a hash function. So they wrote up their inventions as short sentences, and then they scrambled the letters in those sentences to obtain an anagram, and they published those in their scientific journals or booklets in order to claim priority of their scientific inventions, which they were not ready to reveal yet. And then they were later able to show that when I posted this cryptographic message or this cryptic message a few months back, what I meant was this. And then they would have some kind of evidence that they had actually had this idea before others, but without revealing the idea itself. Now, this, of course, in today's terms, what you can do, you can, if you are in the same position as Galileo was in 1610, you can write up your invention or your revolutionary theory in a text document. You can hash the document, and you can publish a hash value in Twitter or maybe in newspaper, depending on how conservative you are and how strong and long-term evidence you want. And then one thing that you can do, you can also publish this thing into so-called hash-linked ledger. So a ledger is an accounting term, meaning a book of accounts where you can only add new stuff at the end, but you cannot edit things that you have already written before, or you cannot remove things that you have already written in there. And a digital ledger can be constructed from hash functions in such a way that when you want to add a new record into your ledger, you take the hash value of the previous state of the ledger and you hash it together with a new record. And this way you obtain a fingerprint that represents uniquely the whole history of the ledger up to that point. You add the next record by again hashing together the previous summary hash with a new record to obtain a new summary hash, and a new record with the previous summary hash to obtain a new summary hash. And every time, if you now hold one of those hash values, then none of this preceding history can be modified without breaking the security properties of the hash function. So assuming the hash function is secure, just holding on to this last value in this the current head value enables you to verify the integrity of the whole previous history. And now, of course, again, if you want to do it in a scalable way, then instead of if you're running an accounting system where you really add your records one by one, this is good. You can do it like this. But if you want to run a timestamping service based on this thing, so if you are a notary that notarizes digitally some important documents, and probably the number of documents that you process is not too large, you can do it one by one. But if you want to be able to build a timestamping service that can be used to timestamp, for example, logs of multiple clients, and the multiple clients may be able to produce a very large number of log records every second, every minute, and then you don't want to do this completely linearly or serially. So one thing you can do is you can process your inputs in batches. So you create a fingerprint every second, and all the requests from your clients that come in to you as a timestamping service provider or this kind of specialized notary, you aggregate them into a local tree. You post the root value of this into your internal ledger, and then you can return to each client this newly updated fingerprint of your ledger and approve that this record was included in this batch that was linked into the history of your system. And so this is a way to do it. And now any client that has one of those fingerprints can verify the complete history, and anything can be verified. Anything that was included in one of those aggregation batches can be verified against this history. So you get again this two-step verification where the fingerprint proves the history, the integrity of the ledger, And then each of the ledger nodes is able to prove the integrity of any of the inputs that were part of this batch. And if you look at it a little bit and think about it a little bit, then this actually is exactly what a blockchain is. So you have the blocks of incoming records, and you have the aggregated hash chain of keeping the history of the records. So this is essentially maintaining this kind of ledger is what Bitcoin does, and maintaining this kind of ledger in a different way without mining is actually what GuardTime does for the KSI blockchain, which provides this kind of hashing-based timestamping service to our clients. So this is one of our core services. This is the blockchain that I mentioned that we started in 2008 before Bitcoin came out. And actually, we are being a little bit more clever about it. So what we do is we do not keep this. Here, why is not moving? Okay. So here, the data structure here is linear. So this is basically a hash function protected linked list. And what we are doing here instead in KSI blockchain, instead of doing this linear linked list, we actually build another layer of Merkle trees. So the linear history of every second or every round or the block commitments is here in the leaf nodes of a binary tree. But we link, instead of doing a linearly linked hash chain, we build a binary tree on top of this ledger also. And this enables us to do this more conservative way of publishing. Every month, we actually take out an ad in Financial Times and print the current head value of our ledger in newspaper. So you can have a physical printed evidence of what was the state of this digital database at this moment. And you can refer your proof of participation back to this physical evidence if you want to. Most verifications of individual timestamps, of course, do not do like this. But what this enables us to do is anybody who is relying on the integrity of this digital database can go every now and then and verify that the database is intact by recomputing what the value according to their digital records is, and checking that it is really what was printed in newspaper a while ago. So this is a very brief summary of how this hash tree aggregation based hash and publish timestamping works in industrial scale. And by combining those two things, this aggregation of incoming requests in each aggregation round, and then this tree-based aggregation of inputs, we are able to provide a proof of participation and proof of time that is based on hash function and links on hash functions cryptographic properties alone, and links back to this physical evidence in the newspaper with a size of about a couple of kilobytes for each incoming client request, up to ridiculously large numbers of requests and for the foreseeable future. So this is a timestamping system that we have been running in production for more than 10 years now. And now we are using this to build a more efficient digital signatures on top of this. And why we want to mess around with all of these hash function based things, one key motivation is that you may have heard that when quantum computers get built, then all of the current crypto will break down. And this is true for RSA. RSA will be vulnerable to attacks by quantum computers once somebody builds a sufficiently large and sufficiently reliable quantum computer. And the same will be the case for LP-based signature systems. And this is because the algebraic properties. So in those systems, there is a mathematical relationship between private key and public key. So basically, there is an equation. If you want to derive the private key from a public key, there is an equation that you have to solve. And the equations for RSA and the elliptic curve-based digital signature systems, they happen to be such that they are infeasibly difficult for classical computers, but they can be solved more efficiently by quantum computers, assuming somebody builds a quantum computer. In case of RSA, the thing that the quantum computer has to do, or rather any computer has to do, is to be able to factor large numbers. So an RSA public key is a product of two large prime numbers. Like if your small prime numbers are 3 and 7, then 21 is a product, and the product would be the public key. And if you know the factorization of 21 into 3 and 7, then from 3 and 7 you will be able to produce a private key. So unfortunately, it turns out that quantum computers would be rather good at solving, or depending on which way you look at it, fortunately or unfortunately, that quantum computers would be rather good at solving these kinds of equations. Right now, the biggest thing that has been practically factored by a quantum computer, as far as I remember, is actually 21. So considering that that this is a result of 10 years of effort, it may seem laughable, but we have seen before that once something gets going, it may develop quite fast. So in order to break RSA for current key sizes, then in current key sizes, when we talk about RSA, where the public key is 2000 bits, then the factors of the public key each are around 1000 bits, which is roughly 300 digits. So factoring 21 into 3 and 7 is a far cry from factoring something that is a product of two 300-digit numbers. But once something gets going, it might develop fast. And on the other hand, getting any new technology deployed into existing infrastructure takes a lot of time. So despite the current generation of quantum computers looking laughable, actually the time to get worried is now. So this is a motivation why we want to do digital signatures based on different technologies. There is a bunch of different ideas out there of mathematical things that are currently believed to be difficult for quantum computers to attack. They include certain kinds of equations on multivariate polynomials. They include data structures known as lattices. They include certain types of error correction codes, and they also include hash functions. So breaking the security properties, the collision resistance and second premise resistance of a hash function is somewhat more efficient on a quantum computer compared to a classical computer. But the difference is not as catastrophic as in case of the algebraic equations of RSA. The attack costs, even with a quantum computer, the costs to break the security of a hash function are still exponential in the size of the hash function output. And this means that hash functions are a good candidate also to base next generation of digital signatures on. And this is exactly what we are trying to do with DLP, which is a digital signature system that we have invented at research team in GUARDTIME. So the idea is that we use one-time keys for message authentication, and message authentication, as we discussed a few slides ago, is symmetric. So you don't have this non-repudiation property, and it also additionally has this problem that if I'm exchanging authenticated messages with somebody else using the hash function-based message authentication code, then we share a secret key. And if I now even neglecting the problem of non-repudiation, if I wanted to show this authenticated message and the authentication verification to somebody else, I would need to disclose this private key. And this means that from that on, there would be a third party who would know the private key, the secret key as well. But whereas previously it was only shared between the sender and recipient, now the verifier also knows the key. And so this means that this private key is no longer, or the secret key is no longer usable for authentication between those two parties. And since we have this problem, and since we already had this hash function-based timestamping system, then our idea was the idea of this BLT signature system is to use time to break symmetry in this message authentication code. In other words, to establish a line of a time boundary where the key is secret and can be used for signing before some time, and after that time it transitions into a public key, a verification key. So the key itself is the same; it doesn't change. Only the logical state or the role of the key changes, and this is based on time. So in order to be able to sign messages at various different times, so for T1, T2, T3, T4, and so on, we can index those elements using the POSIX time T, for example, which is what we do in practice in DLT. So we generate those keys as just random numbers, which we don't show to anyone. And then in order to make the distinction, so if there is a current time here, we want it to be so that these past keys here are only valid for verification. They are no longer valid for creating new signatures. And the future keys, they are valid for signing at some future times. So those I can disclose as a key holder, and those I have to keep secret in future. And in order to make this commitment of which key is valid for which time, what I can do, I can hash together. I take the value of the key, which is a large random number, and I combine it with a time for which it is valid for signing key. And I compute a hash value from those. So again, I combine those two things in hash by hashing them, just like in the hash tree or Merkle tree, to obtain this binding of the key to time. And the logic of why this is valid is the same as why the whole hash tree thing is valid. I can't, after the fact, I can't change either of those without breaking the security properties of hash function. And now I have obtained those key bindings for one-time keys. And in order to obtain one single public key, I aggregate them into a hash tree. And then the root of this hash tree, this is my public key. This is what I publish. This is a commitment. Anything that comes from this tree, properly authenticated, is one of my private keys. And then in order to sign something, a document at a given time, what I do is I take the document, typically I hash it, and then I combine the document's hash with a key that corresponds to the time when I'm doing the signing. So I need to know what the current time is, and assuming I do know that, I can pick the correct key out of my many one-time keys or many signing keys, and I combine. I now compute basically this message authentication code on this document hash using the one-time signing key as the message authentication key, and I obtain a hash and publish based timestamp on this combination of those two. And this timestamp proves that I operated on this document using this key at a given time. And in order to prove now that this is a valid signature, the second part that I need is I need this hash chain that links this pair or this binding of this key to the time to my public key. And now these two hash chains combined, these form a signature. So this hash chain here proves when was the time when the key was combined with the document, and this chain here proves when was the time when the key was supposed to be used for signing. And now if the time recorded here and the time recorded here in the timestamp, if those two match, then by definition the signature is valid. If they do not match, then by definition the signature is not valid. And this definition allows us to publish this key as part of the signature, because the time when it can be used for creating new signatures, this is already passed. You can't. So anybody who gets this key as part of my signature, they cannot anymore create new signatures for it, because if they would try to pull this key out of the signature and try to combine it with another document, then the timestamp that they would be able to get would contain a time that is too late. The time in the timestamp binding the old key to the new document is recent, but the binding here in this key pair, this is older. So the time here is older than the time in here. There is a mismatch and the verification fails. And this means this is why you can't reuse a key that you have extracted from an existing signature to create a new forged signature. So this is how it works. So keys are pre-generated for each possible signing time. And this kind of scheme is suitable for computers that have reasonable computing power, because you need to generate a bunch of keys in advance, quite large number. And you need to have a reliable clock to know what the correct time is, and you also need a reliable network access to access the timestamping service. And I have a question in what happens if I just change your computer time? So you basically you do not do a security attack on me in sense that you will not be able to forge signatures. You will do a denial of service attack on me, because when I going back to the previous slide, when I combine my document with a key and get a timestamp on it, before I compose a signature and emit it, I do verify also that the time here and the time here match. And if you cannot, if you only change the time in my local computer, then I have used the wrong key, and I have produced an invalid signature, and I will just destroy the whole thing and will not publish anything, will not send out the signature. And so in order to be able to attack me, you need to be able to attack the time in the timestamping service. And this is a core business of the timestamping service. And why you cannot do that, this is a topic of separate discussion, which I can't go into now. But again, very, very good question. Thank you. So where is my keyboard focus? Okay. So these are the properties. And this version of PLT signature scheme is suitable then for applications that run on server and have to support many clients, because they need to sign often. And so for them, and then for them, they can generate those one-time keys for all possible time slots. And now it seems we are running out of time. So there is another version of signature scheme in this PLT family, but unfortunately I don't have time to explain it anymore. So I have to jump to the end and give you the references. So the PLT-TV is a version of this PLT signature scheme from this family, which I just described. There is an academic paper out describing it in more detail with security proofs and everything. And the other scheme, which I did not have time for, was PLT-OT, which is more suitable for small devices, personal signing devices that are used rarely, and like smart cards or perhaps phones also. And the description of that scheme, second scheme, in more detail is we have another paper out on that. So I invite you either to read it, or if you are interested, I will hang around in Discord and in Remo after the talk. So if you want, we can take it offline. But now I'm already a couple of minutes past the time limit, so it's time to say thank you, and maybe one last or a couple of last questions. And if not, then again, also for questions that you think of a couple of minutes, or for any questions that you think of later, I still hang around, or you can also send me an email or catch up on Twitter. So thank you for your attention, for your time. I hope you learned something useful from this presentation. I certainly enjoy talking about this stuff, because I do find it interesting. And yeah, I hope it was useful for you as well. Thank you.